from 0 to 2 pi of 20 times cosine 2t. And now we can integrate this. We'll have 10 sine 2t from 0 to 2 pi, which is what? When we plug in the limits?
0.
0. All right. So, all that for nothing. But if you recognize, this is something that's good to keep an eye out for. Notice each component function of this vector field omits the corresponding variable. Here we have no x, here we have no y, here we have no z. In fact, f is actually the gradient of this function little f, where little f is equal to x, y, z. Because if you differentiate this with respect to x, you get yz. You differentiate with respect to y, you get xz, and so on.
So if each component there is missing its corresponding value, like you said, x, y, and z, then we can assume it's the gradient, and the gradient's always 0?
We got to be careful with what's left.
Okay.
Yeah, it's something that suggests that because this is something that's easy to integrate with respect to x.
Right.
You just put an x there. And so then if you find that, okay, well x is here, but now y is missing, so
all right.
Yeah. So when you have missing variables like that, and it makes these really easy to integrate with respect to x, y, or z, then that's like just maybe it is a gradient of something. So it's a signal that's worth checking out.
All right.
Yeah.
Are there any other helpful ways to determine whether or not it's the gradient of?
Okay, yeah, here's another. If you see a function in one component and you see its derivative in another component, like for instance, if you see, for instance, tangent of z in one component and secant squared z in another component. Okay. So that's a hint that maybe that it's a derivative of something. So yeah, there's certain clues like that that make you wonder. All right. So if you see that this is actually a conservative vector field, well, what do we have here? This is the line integral of a conservative vector field over a closed curve. It's 0. Yeah. Because this, or another way to look at it, this is the integral from A to B of the gradient of f, evaluate r of t dot r prime of t dt, and then you apply the fundamental theorem of line integrals, which says that this is f of r of b minus f of r of a. But this is a closed curve, so r of b and r of a are the same point. So it's 0 for that reason.
So, when you evaluate it the other way?
So this way?
Yeah, the first where we did it together.
Oh, yeah.
What's the integral of cosine of 2t? I must have forgot that.
Oh, so the integral of cosine of 2t is going to be sine 2t over 2.
Okay.
So integrating the curl over a surface by Stokes' theorem is integral to the line integral of the original vector field over a boundary. So you might find that if this is easier, then go ahead and do that. So questions about this one? So some of the nice things, one of the nice things about surfaces is the surface could be incredibly complicated. You could have some, I don't know, something that's glove shaped, for instance. I'd imagine trying to parameterize something like that. And then that's a nice simple circle for a boundary. Just integrate over that. So Stokes' theorem lets you do that. because it doesn't matter what's going on in here. It's equal to a line integral over a boundary. So this actually makes a very interesting statement about what Stokes' theorem is saying. That you could have the same vector field f, and you could have different surfaces with the same boundary. And the integral has to be the same. So for example, just to graphically illustrate what's going on. So let's have some curve sitting somewhere in space. And then we have this surface S1 sitting on top of it. And then we have another surface I guess the whole thing looks like a very deranged tooth. Well,
it's got a cavity or something.
I did have to take in my cat to have her teeth cleaned. So maybe I had tooth on the brain. Yes. There you go. So.
Does your cat have deranged teeth?
No, but she is deranged.
Okay.
Okay. I tend to do my grading here because she eats assignments. So. Yes.
So, could you define your own, I guess it's called line integral, anywhere on an object like that? Say if that circle is higher or lower, would it Stokes' theorem still work like that?
Oh, well, yes, it would. Yeah. So, in other words, like if it was up here instead.
Yeah.
Yes. But I haven't made an actual point yet. But when I do make my point, it will apply.
Okay.
Okay. Now, don't forget the orientation. Right? So we're assuming. So this curve has. We can orient it in two different ways. So what's happening in this case is the line integral along this curve. As long as we keep this counterclockwise orientation, is that the line integral of a vector field over this boundary curve C is equal to the surface integral over S1, and then here's S2 down here, of curl F, dot product with the normal, and it's also equal to same integral over S2 with this surface's normal vector. And any other surface you could define that happens to have the same boundary.
So that's the only thing that changes, is I guess the magnitude of the normal vector?
What happens is well, certainly the normal vector can have a very different character on S1 as opposed to S2.
Right.
But what's happening is, in effect, because of the different characters of surfaces, because this normal is going all different directions, there can be some cancellation there, which is why I could have something where maybe I have C just being the boundary of this tip. So we're integrating over this really tiny surface as opposed to this really big one. But it still doesn't matter,
So
because there's enough cancellation of curl with normal as you go navigate all the way around the surface that the two integrals end up being equal.
It's almost like it's holographic because every part of it contains the information of the whole thing.
In a way, yeah.